Hello everyone. In today's presentation, I will be talking about electromagnetics in cameras and briefly covering infrared technology. I will do so by exploring the intersection of electromagnetism and imaging advances. But first, before we get into the lengthy details, allow me to enlighten those who don't know how cameras actually work, starting with there being two types of cameras known as film and digital SLR, or DSLR for short. We'll focus on DSLRs for right now. There are two types known as mirrored and mirrorless. The DSLR mirrored camera works by light entering the camera lens and reflecting off of a mirror inside the body that the photographer then sees in the viewfinder. They then take the picture, which means that the mirror swings out of the way and light hits the digital image sensor. This information the sensor receives then gets sent to an SD card ready for you to view, edit, and print. A mirrorless, on the other hand, is exactly that. There is no mirror reflecting, and thus the light hits the sensor directly. Now, before we move on to the actual schematics of what it means to have electromagnetics in cameras, I first want to bring up the camera basics. Now, of course, I can talk about the difference between lenses, body, sensor, and all that, but I just want to bring up the main three principles that every photographer needs to know in order to operate their camera. The first thing on our list is aperture. This is the size of the hole in your lens measured in what's called f-stops, such as f1.8 or even f14. The range of your aperture depends on the lens you're using, but what aperture actually controls is the amount of light allowed into your camera. A wider aperture like f2.4 allows more light to reach the sensor, which then affects the exposure of the image. You can also control the depth of field of your image, so the smaller the aperture, the greater the effective depth of field. Smaller aperture is what you'll usually see portrait photographers using, as it blurs the background but keeps your subject in focus. The next thing we'll talk about is shutter speed. It controls the duration of the camera shutter to stay open before taking a photo. It is measured in seconds or fractions of a second, which can also affect the image exposure, just like aperture, but also affects the motion of the image. So higher shutter speed, such as 1/3200th of a second, is usually seen in sports photography, where a subject is moving really fast and requires a fast shutter in order to capture the subject in focus and in motion. The downside to a faster shutter is a shorter exposure, which means less light in your image. The times you would want a longer exposure, like 1 full second, would be in nighttime photography, as you want as much light as possible to enter your camera. This is where star photography usually uses long exposure to capture the night sky. Last but not least, there's ISO. Now, ISO pretty much wraps up the other two principles of exposure by controlling the amount of light that your camera lets into your sensor to control how light or dark your image appears. In brighter lighting, lower ISO is the best, such as ISO 100, but when less light is available, higher ISO is needed, like ISO 800. The downside to higher ISO, however, is that it can result in grainy or noisy photos, which can reduce image quality. Overall, all three work with each other to make sure that your image is captured to the desired exposure and quality. Now let's break down the math behind that. As long as we get a basic understanding of what is happening, I think we can move forward with that knowledge. Some of the basic functions of a camera can actually be seen here, starting with exposure. It is defined as such, where I is the intensity of the light exposed and T is the time in seconds. Shutter speed is one of those variables that controls light exposure and actually is mapped to a variable called time value, or TV. And aperture is defined as the focal length divided by the diameter of the lens. The result is the light intensity determined by the choice of aperture used to take a photo. It is measured in f-stops as brought up just before, which is mapped to a variable called aperture value. I mentioned earlier that each core principle relates to how exposure is captured in an image. It can be summed up as being called an exposure value, which is a combination of intensity of light and duration. Now, I'm not saying that every photographer must make these calculations in order to take a picture, but it just shows that each variable can be broken down and solved if necessary. Each solution would give the photographer the key settings to obtain the correct light exposure design. Okay, now that that is out of the way, we can talk about how the electromagnetic side of cameras comes into play. There's really four areas that are worth mentioning, starting with electromagnetic shutters, autofocus, image stabilization, and wireless data. The first on our list is electromagnetic shutters. Electromagnetic shutters makes use of electromagnets to control exposure times that allow for faster shutter speeds, which means shorter exposures. So when you take the picture, the shutter cranks open and the mirror flips up. When this happens, it pulls the front curtain of the shutter, exposing light to the sensor. It then moves the rear shutter out of the way, and electromagnets hold each curtain in place until the camera releases them, aka the exposure time. When the shutter closes, it is released by another magnet. This drops the rear curtain covering the sensor, and thus you get your picture taken. So, if you see to the right, I have a picture of what looks to be an open shutter, showing what is the mirror inside the camera. And down below it, you can actually see a GIF, or GIF, whatever I'm going to call it, of how the shutter moves the slides over, and that is actually being controlled by the electromagnets. Outside of the shutter, there is also the autofocus. Autofocus makes sure that it keeps your subject in focus and includes motors that use electromagnets to adjust the focus. The way this works is through what are called voice coil actuators. They consist of a permanent magnet and electrical coil. A current running through the coil assembly interacts with the magnetic field, which generates a force factor that is perpendicular to the direction of the current. The force generated is proportional to the cross product of the current flowing through the coil and the magnetic flux of the magnet. It is dictated by the Lorentz force equation F equals B times I. This type of motor is actually what replaced the older helicoid barrels, which originally worked by rotating the barrel and thus moving the lens forward or backward. The auto part is where we see the motor and lenses eliminated the input of the photographer. Instead, the lenses slide up and down on posts and thus focuses your image for you. To the right, you can see the top, we have an image of what an actuator coil would look like. You can see the coils right there and the permanent magnet, which combined will actually change the focus for you on its own. On the bottom right, you can see that the helicoid coils would have looked like, which has tiny grooves on it that rotate and would have actually bring your camera into focus. With the newer autofocus, you no longer have to have that human interaction behind it, which means faster and more precise focusing. Next, I want to talk about image stabilization. Now, image stabilization comes from electromagnetic actuators that compensate for camera movement. They are most known for what is called optical image stabilization. Now what this means is that inside the lens there are specialized gyroscopic sensors that can tell when the image is out of alignment with the sensor. Small electromagnets work together with these specialized gyros to correct the angle of the lens or the image sensor depending on the source of the system. The small actuators receive signals from the gyroscope and move the lens element in the opposite direction of the detected camera shake. In the end, this helps prevent shaky movement that could be caused by the photographer or the ground when using a tripod. Last but not least, I can't help but talk about wireless data. Cameras make use of Wi-Fi or Bluetooth as a way to send your images to your phone or computer. It uses radio waves for sending these images, and we have already seen a few presentations on the concepts of Wi-Fi and technically Bluetooth, so I won't spend a lot of time explaining this. However, I will briefly mention that Bluetooth communicates with devices by using ultra-high frequency radio waves. These electromagnetic waves have frequencies of about 2.5 GHz, where radio waves result from an alternating current in the wires. When Bluetooth devices are close enough, they can connect via a small computer chip that emits these special radio waves. When involving all this technology, there's of course going to be effects from magnetism on the camera itself. How, you may ask? Well, magnetic properties can influence how they interact with electromagnetic fields, and magnetic interference happens when a magnetic field interacts with other conductors, leading to distortion in images. Common sources can be seen in power lines, transformers, phones, tablets, and even watches. So a lot of this must be considered when a photographer is taking their pictures, as they must stay aware of the environment they are in. Now, moving outside the field of basic cameras, I want to talk about what are electromagnetic cameras as a whole. And what I mean by this is that these are imaging devices that detect electromagnetic radiation across different wavelengths, not limited to visible light. Some examples are infrared cameras, visible light cameras, just like I talked about, UV cameras, and X-ray machines. Now, before we move on to what exactly is infrared and all of that, I just want to break down what is the electromagnetic spectrum. The electromagnetic spectrum pretty much consists of radio waves, microwaves, infrared, visible light, ultraviolet, and X-rays/gamma rays. And all of these radiate on their own different level of frequency. This can range from what we can see, which is visible light that can be captured through regular cameras, to things that we can't see, like X-rays and gamma rays. Some key components to how infrared cameras and electromagnetic cameras work are sensors, optics, and processing units. Sensors are specialized detectors that respond to specific electromagnetic wavelengths. Optics are lenses and filters made specifically to focus and filter desired wavelengths. And processing units convert the sensor data into viewable images. Now this is the basic foundations to your everyday camera and what I was going over earlier. However, in this case, we're going to be capturing a little bit more complicated images versus just pictures of birds or whatnot. So, how do they work? There are two sections to cover in the basics to how infrared cameras work: detection and image formation. The first being detection. This is where thermal sensors can detect heat emitted as infrared radiation. There are also photon sensors, which convert incoming photons into electrical signals. And then all of those are combined into the image formation, where signal processing takes place. This is how the image actually takes form. And as you can see here to the left, I have a picture of what a thermal sensor looks like. While to the right, you can see how image formation takes place. You have incoming light being read with a wire anode mixing with an electric emission and a photoelectric cathode, which all together works to create the image that you're seeing before your eyes. Okay, so now let's just break down the basics of infrared. First of all, infrared captures images based on infrared radiation emitted or reflected by objects. This is what you see hunters or military using to see objects or life under the cover of night. There is also thermal imaging, which detects IR radiation and is typically used in temperature mapping. There are cases of this being used where people use thermal imaging in order to capture the interior of buildings as seen in the picture to the left to determine certain levels of heat. This can come in handy to prevent overheating in mechanical situations or electrical circuits to help prevent equipment failure. Now, there are also near, mid, and far infrared cameras, which are used to detect light or heat at different wavelengths in the infrared spectrum. Each length has its own purpose, such as mid-infrared being used to penetrate the human body to see skin, muscle, and tissue circulation. As you can see in the picture bottom right, there is a light spectrum that even skin and tissue follows, so infrared helps see the details that the human eye cannot see. So what are the applications of infrared, and how are they used today? Well, there are four pretty big applications, starting off with a major application, and that is security and surveillance. Now, security and surveillance makes use of the technology in the form of night vision abilities. This can be seen in security cameras and even military aspects. The biggest application I would say is in medical imaging in the terms of X-rays. This works by electrons being accelerated under a potential difference and thus is turned into electromagnetic radiation. High voltage is accelerating electrons toward a metal target, which causes them to rapidly decrease, which in turn releases energy in the form of X-rays. There are also industrial inspection use. Industrial inspections use IRA, aka infrared radiation, to identify heat leaks or faults in electrical systems. So imagine you have a heat leak that you're not able to see with your own eye, but if you use an electromagnetic camera or infrared, you're able to find and prevent any further damage from being done. Then there is environmental monitoring. This uses IR to monitor wildlife and plant health. It can detect things such as volcanic activity, marine life, and climate change. We all know that nothing is more important than the health of our own world. This pretty much concludes the presentation, and I hope this was able to bring some more insight into how electromagnetics are involved in not only just the basis of cameras, but can also be seen in the technology of infrared and even electrical imaging. Thank you very much.